Derivatives of exponential functions. At this stage, we know how to differentiate functions of the form y is equal to ax to the n, and of course sums of that type of thing as well. When we differentiate, we get dy dx is equal to nax to the n minus 1. Different types of functions have different differentiation patterns to this. If we consider y is equal to a to the x, now note here that x is the power. We don't have x to a power, so this is a different situation. This has a differentiation pattern that we can investigate from first principles. Please note that this does not differentiate in the following way. It is not xa to the x minus 1. Note the difference I mentioned just now. The x here is the index, whereas here the x has an index, which is a number. So it's a different type of function. It doesn't differentiate in the same way. So let's look at f of x is a to the x from first principles. So the graph would look like this, at least it will if a is greater than 1. So let's have a general point here, x a to the x. Remember, if we substitute x into here, we get a to the x. And then a bit further away, we have this point here, x plus h. And then substituting x plus h into our function, we get a to the x plus h. And here's the chord between them. So if we form a right-angled triangle like so, delta y over delta x, that's the difference in y, so the delta y would be just here, and the delta x is here, and of course delta x is equal to h. Delta y over delta x is f of x plus h minus f of x over h, and of course we know that f of x plus h is a to the x plus h, and f of x is a to the x. So we're just using the y coordinates from here and here, and dividing by h. Now, remember our index laws. So a to the x plus h is just a to the x multiplied by a to the h. Remember, we would add the indices in this situation. So we can split this a to the x plus h to a to the x, a to the h. And then we have a common factor of a to the x which we can take out. And that gives us a bracket which is a to the h minus 1. Now, following from that, we know that dy dx is the limit as h tends to 0 of delta y over delta x. So it's the limit as h tends to 0 of this expression just here. Now, h going to 0 is not going to affect a to the x. It's independent of h. So we can bring that out of the limit in front. So that's a to the x, limit as h tends to 0 of a to the h minus 1 over h. So provided this limit exists, in other words, we can actually get a value for it, the differential is this constant. So this will evaluate to a number multiplied by the original function. Let's look at the value of this limit for some different constants a. So we're going to put some different values of a in and see what happens. And I've evaluated these on the calculator. The calculator can do limits. In fact, let's just drag the calculator in and let's look at where we'll find that. And I think it's in Math 2. And there it is. There's the limit function just there. So we can put in h tends to 0 and put an expression in here. And I've done that for a is 2 and a is 3, and I've also done it for a is equal to e, and we know that e is an irrational number, 2.718 roughly. So I shouldn't have put that there. It's just so e to the power 1, 2.718 and so on, but it's an irrational number. It goes on forever, a bit like pi. And when we actually use e in here, we get 1, and this is absolutely crucially important. Notice for 2, a is 2, we get ln 2. That's the natural log of 2. And for a is 3, we end up with the natural log of 3. So we'll come back to that in a moment. So it follows that if we differentiate 2 to the x, we get 2 to the x ln 2. So over here we had a to the x multiplied by this limit. On the calculator we've identified the limit is ln 2, so it's 2 to the x ln 2. And if we differentiate 3 to the x, we get 3 to the x ln 3 in exactly the same way. And the most important of all is that if we differentiate e to the x, we get e to the x. So this one, as I've mentioned, is really important. We're going to use that a lot. The function y is equal to e to the x differentiates to itself. So dy dx is e to the x. But of course things like chain rule and so on apply to it. We can use the product rule with it, we can use the quotient rule with it, and that's where we're going to.